Hi everybody, it's me from the future. When I first recorded this day 10 of Advent of Code, I forgot to put the microphone in front of my face. I only got as far as reading out the problem, so I'm gonna read this through, and then I'm gonna jump back to yesterday, so you can take over from there. So, my name is Jacob Tomlinson. I'm working through Advent of Code on the GPU. Try and see how much of Advent of Code problems I can write in Python in a way that makes use of the GPU. So let's read through day 10's problem. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared, you make a list of all the joltage adapters in your bag. Each of the joltage adapters is rated for a different output joltage, your puzzle input. Any given adapter can take 1, 2, or 3 jolts lower than its rating and still produce its rated output joltage. In addition, your device has built-in joltage adapter rated for 3 jolts higher than its highest rated adapter in your bag. If your adapter list were 3, 9, and 6, then your built-in adapter would be rated 12. Yeah, because 9 is the highest in this list, and it is 3 higher, so it would be 12. Treat the charging outlet near your seat as having an effective joltage rating of 0. So just start from 0. Since you have some time to kill, you might as well test all of your adapters, which you wouldn't want to get to the resort and realize you can't even charge your device. If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? For example, suppose that in your bag you have adapters with the following joltage ratings. Here's a list of adapters. With these adapters, your device's built-in joltage adapter would be rated at 19 plus 3, right? 19 is the highest number in this list, so 19 plus 3 is 22. And because adapters can only connect to source 1 to 3 jolts lower than its rating, in order to use every adapter, you'd need to use them like this, right? So we start at 0. 0 is also not in this list, right? So, yep. The charging outlet starts at 0, and then you want to step through each adapter in this list in order, and then eventually end up at 22, which is the rating of your device. In this example, when using every adapter, there are 7 differences of 1, right? 7, you know, because you've got like 5 and 6 and 7, right? So there's a difference of 1 between each of those. 7 differences of 1 and 5 differences of 3. Some of the others where you're going from 7 to 10 is a difference of 3, right? So you've got 7 differences of 1, 5 differences of 3. Here's a larger example. In this larger example, the chain that uses all the adapters, there's 22 differences of 1 and 10 differences of 3. Find a chain that uses all of your adapters to connect the charging outlet to your device's built-in adapter and count the joltage differences between the charging outlets. The adapters and your device, count the joltage differences between the charging outlets, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? So for part 1, it's going to be 7 times 5. And then for part 2, it says we've got 22 and 10. So it'll be those multiplied together. And yes, so I think you actually got a sneak peek of the answer, which we'll go through and solve now before moving on to part 2. But yes, apologies for the recording mess up, and I will now hand back to me from yesterday. I feel like for the first part at least, the fact that it can only use the adapters are only rated for 3 jolts higher. No. Yeah, any given adapter can take an input 1, 2, or 3 jolts lower than its rating. But I feel like that's a bit of a red herring, at least in this first part, because they're saying you have to use every adapter in your bag, which must mean that every adapter in your bag is within that range. Otherwise, it makes no sense. Which means if I sort this list, it should give me this order, right? I would have thought. And then what I need to do is work out their intervals, right? Just count the intervals between these things. Okay, let's have some code. Yeah, we'll have, this is day 10. and we want to, I'm just going to open up a previous solution just so I can copy some bits from it. So I'm going to process our input data here. Right, yeah, we'll start with NumPy. So let's import NumPy as NP, and then we'll write ourselves a function. This is going to be very similar to yesterday because yesterday was also a 1D array of integers. Let's come back to day 10. I'm going to make a new file and call it sample as well. Sample. So this function from yesterday opened up our file, and then for line and read lines, just read in a 1D array, right? Which is exactly the same as what we want to do today. We want to read in a 1D array of integers. So that read data function from yesterday will be fine. So let's have our sample input is going to be read data of sample, which looks like that, but that's because I need to actually populate this with our sample. Yeah. Again. Okay. So now we have our array. The first thing we need to do is we need to take the max of our array to work out our, I don't know if we care about this, right? But that's it, right? That's data processing. Anyway, data processing done. Let's start part one. Part one. Okay, so the first thing we need to do is our, what do they call it? The built-in adapter. Right, so let's say built-in adapter is going to be the max of our sample input plus 3. Let's get rid of that day now. Plus 3. Our built-in adapter is now 22. Yeah, okay. That's 22 for here. 22 is the highest rated adapter. And because that needs to go in the list, so we actually need to append that to the list. You need to say sample input. Can you append to a NumPy array? NumPy and type it all. NumPy array append. Oh, you just do np.append array and values. And the values are a list. Okay. That's fine. So we can say sample input equals np.append our sample and our built-in adapter like that. And we should be able to have a look at our sample input is now got 22 on the end. Great. And then we need to go through, we need to sort it. That just didn't in place sort. We've now sorted the input. So it's 1, 1, 4, 5, 6, 7. Let's just make sure this goes. We go 1, 4, 5, 6, 7, 10. Yeah, 11, 12. And after 12 it's 15. Then 16. Then 19 and then 22. Yeah, okay, so sorting the array makes the most sense. And then we want to work out the differences, right? So we could do this with number, right? This would be a reasonable use of mapping over. So we want to map over the array. Yeah, so let's do import from number import CUDA. And I'm just going to go back to yesterday and copy some boilerplate stuff. Let's do something like this. We need to do, this will be calculate intervals. I mean, there might be a built-in for doing this, but I want to do this way just so we can see it. So calculate the intervals, and this will be our joltages. Why not? Let's call it that. So we're going to step over the length of that -1 because we're only ever going to be comparing to the next one, so we don't care about the last. So we're going to step over that, and let's just do output position equals 1, or position. My favorite little function to do just to test that I've done things right. Then we need our threads per block and blocks per grid. So do 128 just because that's a good number. The blocks per grid is this, right? That needs to go there. Oh yes, this is actually going to be called joltages. Joltages. So the sample input. Let's just come through and do that all the way through here. All right, let's go like that. Oh yeah. That. Oh, there's joltages. 22 and 22. That's now sorted. Okay. Then we define our function on that blocks per grid, and then the last thing we need to do is we need an output array that we're going to pass in and update values in, because from the GPU we could only update arrays. We can't return anything. We're going to make this the length of our joltages -1 because we don't care about the last one, and calculate intervals, our joltages, and then let's just have a look at the output. This is a bit more complex from yesterday's solution, but the output here is just our position, right? Because we're counting through our positions. But now what we want to do here actually is do output position is equal to joltages position +1 minus joltages position. That should give us our intervals, right? We've got the 3s and the 1s like this. I wonder, actually, thinking about it, because part of the point of what I'm trying to do here is do as much on the GPU. I could probably use CuPy instead of NumPy here, just to make these things happen on the GPU, right? CuPy is an equivalent to NumPy that runs on the GPU, but I might come back and tweak that in a minute. Because we're not doing a huge amount of work here, right? We've just written a little CUDA kernel that calculates our intervals. But now we need to count. In this example, when using every adapter, there are 7 differences of 1, and we probably want to use numpy.where, right? So we want to do 7s is going to be np.where output equals 7, right? And this will be their indices. I think I did a where yesterday, didn't I? np.where. Yeah, no, that's fine. 7 differences of 1, 5 differences of 3. This would be 1s. I'll put it as 1. Yeah, so that's all the positions where it's 1. Position 1, position 2, position 3, not 4, position 5, position 6, not 7, position 8. Yeah, that makes sense. And then 3s is going to be np.where output is 3. Let's unpack those well, just because where gives us a tuple. And then we can do a length on that. Length of 1s, 6, and length of 3s is 5. Okay, that's wrong. What's wrong? There are 7 differences of 1 and 5 differences of 3. Something has gone a little bit awry here. 3, 4, 5, 6. I mean, that makes sense. Let's just have a look. Oh, 0. We haven't got the 0 as well. So we need to do right back at the beginning. It said we need to assume that we're starting from 0. So we need to add 0 in here, and then sort them. Oh, let's start again because I'm appending too many values. And then we'll go through again and do this again. But we should have now 7 and 5. Of those. There are 7 differences of 1 jolt and 5 differences of 3 jolts. So here's a larger example. Okay, let's just change the sample up for this sample. See how our logic's doing. Sample, put that one in instead. In this example, you have 22 and 10. So let's just go through and do that. So fine, 22 and 10. Good. So now let's just get the actual puzzle input. This. Oh, wrong day. Okay, that's our actual puzzle input. Let's just change this to input that. The bigger array. Do exactly the same code again. We had 3s and 1s, and it said what is the 1 jolt differences multiplied by the number of 3 jolt differences. So this is actually going to be that times by that is that number there. That's the right answer. Good. Okay. Part 2. Completely determine whether you have enough adapters. You will need to figure out how many different ways they can be arranged. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect will still apply. The first example above, the one that starts with 16, 10, 15. Oh, the first example, 16, 10, 15. Okay. Supports the following arrangements. Okay, so you can just miss the sum, right? So first example above, the one that starts what's following arrangements. You always start from 0, and 1 and 4. Then 5 and 6 are both valid. So you've got the 5s and the 6s. Oh, and the 7s are also valid. But then, yeah, some of these are just missing some. The charging outlet and your device's built-in adapter are shown in parentheses. Given the adapters from the first example, the total number of arrangements that can connect to the charging outlet of your device is 8. The second example above has many arrangements. Here are a few. The total number of these adapters, in total this set of adapters can connect to the charging outlet 19,000 times. You glance back down at your bag and try to remember why you bought so many adapters. There must be more than 1 trillion valid ways to arrange them. Must be more than 1 trillion. That's like highlighted, right? So there must be more than 1 trillion. Really, there must be an efficient way to count the arrangements. What's the total number of distinct ways you can arrange the adapters to connect the charging outlet to your device? Well, I mean, typically what I've been doing so far with this is brute forcing on the GPU. I'm wondering how to approach this actually, because I don't think we want like branching logic. We could do some branching logic, right, where you step through and you go, well, 0, how many valid options are there? Oh, there's 1. Next, how many valid options are there? Oh, there's 1. How many valid options are there? Oh, there's 3. So let's now branch into those 3 and keep going, right? But it means that you're going to branch and branch and branch out like that. It's also maybe a graph problem in that you have these adapters and they have edges. Just curious, I'm just going to search network X total routes from like A to B, right? All simple paths. All simple path is a path with no repeated nodes. Yeah, maybe this is a way of doing that. Why not, eh? Let's jump back into graphs again, because graphs are fun. Part 2. This is probably going to be a separate implementation to what we had before, in that we're going to want to loop through the... I'm just thinking, right, let's go back to our graph problem from the other day. Is it 8? No. 7? Yes. I'm going to try to do this in cugraph today. Actually, let's see if cugraph has a cugraph all simple paths. Cugraph's not especially Googleable, is it? Cugraph. Sorry, I thought I was going to sneeze then. Maybe I will shortly, but we'll see. Cugraph. Cugraph docs. Okay, maybe this is. So slight tangent, but from the other day, I did this with just Network X, not on the GPU, and found a way, to do it, but then couldn't find the equivalent API in cugraph. I ended up raising an issue on cugraph just to say, how could I do this? And they said, there is a way to do this. You do it like this. Maybe we should add equivalent functions as we have in Network X. So maybe this is another one of those situations. Because a lot of these terms just mean nothing to me. Whereas this kind of makes sense, right? Generate all simple paths in the graph from graph G from source to target. A simple path is a path with no repeated nodes. And if I have a digraph, you can only go in one direction. If we have a digraph, I feel like that makes sense. So let's make ourselves a new thing. We want to generate a graph, don't we? So let's have some bits of code from here. Let's just start with Network X for now. Network X. And then we need a new graph. That. And then we've got for ruling rules like this. What we actually want to do is for adapter in, what did I call my array? Voltages. They're adapters really, aren't they? I should have called them adapters. For adapter in joltages. I almost want to do the same thing, right? Where I map over the pairs and add the edges. No, I want to do for adapter in joltages. And then for adapter in. I'm going to put that code there and just go like that for a second. For adapter, I'm going to say for I in joltages, or J in joltages. So we're going to step through each one, and we're going to then step through each one, and we're going to say if J is greater than I and J is less than I plus 3, less than or equal to I plus 3, then add an edge, right? So graph.add edge I to J. No, wait. I think I can get rid of all of that. Let's read data. No. I'm actually going to play around with this a little bit. I'm going to say our built-in adapter is that here. And then our data going to append 0 in the built-in adapter. And then we're going to sort it. And then we'll return it. Right. If we do that, actually, we'll get our full data input here. So then I can just clean out some of this, right? And this is just our code for doing that. And I might even. No, I'm gonna leave that there. Then let's get our data here. Let's just say joltages equals that, and we'll read in our sample. Let's actually have let's make a new file and call it sample. No, let's rename this one. Rename this one sample2. and then have a new file called sample. Put our first example back in. So let's put that one in, a little sample. Yeah. Right, so we're going to read in sample. Let's construct our digraph here as well, like this, and then our graph has these edges, right? So look and make sure that we're going the right place. So and joltages. Have a look. What does joltages look like? 0, 1, 2, 3, 4. That's not right. Sample 2. Oh, that would be why. Move that up there. Rename that sample. This is just me being silly. Rename this sample 2. Put that in there. There we go. Me putting stuff in the wrong place. There we go. We've got 0, 1, 1, 4, 4, 5, 5, 4, 6, 4, 7, etc., etc. Okay, and then I can do all simple paths. This, and say this would be graph. This will be min of joltages. We're just trying to get from the start point to max of joltages. Max joltages. Let's hope we can ignore that variable. What happens there? Oh yeah, network x. Network x dot all paths. Here's a generator. If I cast that to a list, we get this list here, right? All simple paths, which looks very similar to this list here. Good. Then if I do a length, if I do the length of that, it tells me 8. And this here tells me that that was 8 options. Right, so let's try doing, let's put this in the function. Let's say def calculate paths file name. And then let's return that. Return that. That'll be file name. Let's go calculate paths. Let's delete that. Then if we do calculate paths on sample.txt, we get 8. If we do this on sample 2, we get 19208, which is here 19208. And then if we calculate this on our input, what's going to happen? Going to think for a while. Yes, this is a graph problem again. And we're waiting, right? We're on day 10 of Advent of Code. This is the longest I've waited for anything to run. So actually, I mean, I don't know what I'm waiting on. I might be waiting on this. I probably am waiting on that. But yeah, maybe now we need to move to the GPU for doing this all simple paths. Let's have a look. Find the distance and predecessors for a breadth first reversal of a graph. The shortest path single source shortest path. The distances and predecessors for shortest paths I don't want a shortest path though. I want all paths. We're really just chugging here, waiting for this all simple path. Like I said, there's like a billion things to do or something, which is where we would benefit from some GPU work here. I'm like on the fence. Like, do I wait? Do I not wait? As far as I know, NetworkX is implemented in pure Python, which I'm guessing means it's going to be a single-threaded, you know, thing that's just chugging away. No idea how much memory it's using. Between the centrality, I don't know what that is. Okay. Between the centrality is a measure of the number of shortest paths that pass through a vertex. If I go all simple paths, return anything. It's the right call. It's what I want to do. I think I probably want to raise another issue on cuGraph just to say how do I do this, because I assume this is here. It's just how do I get there? Degrees us from edges, get 2 hop neighbors, has edge, is by part type, look up number of edges, number of vertices, out degree, 2 undirect, no. Add internal vertex ID. No, this is all kind of thing. Right, this is just me sitting and reading and thinking. I'm like, there's a small part of me that's like optimistic that this will finish, and I'm guessing that there's probably a better way of doing this, right? There's like a more computer science way of doing this, and maybe I should. While this is running, let's think about that, right? So we're counting the number of routes. Maybe I don't need to actually go through those routes. Maybe I need to do something like from, oh yeah, I wonder if that's it, right? We go through and say from this point, how many points are there? Maybe that's it. Right, let's stop. Make it stop. Stop. That was taking ages. That's the thing we could do, but let's just try one more thing. If we just do basically this, right, for this and this, I indultages for J indultages, if I want like a number, I want like a counter, right? So for I indultages, we can have like next points is going to be 0, and if that is there, the next points plus equals 1. So then what we want to do is like have like a let's just think about this. So from here, from 0, which is in here, so from the first point, I want to say how many points are available next. So it will be, let's have our counter equals 0. So I guess it's how many times does it branch? That's what we want to work out, isn't it? Actually, counter is 1. We're always going to start from 0. And then branches, let's call this branches equals 0. Okay. And then we want counter times equals branches. Yeah. And then joltages is going to be that. And then what's our counter at? 0. If branches. That's given us 12, which is not the right answer. The answer was 8. So it needs to be plus equal something, doesn't it? Plus equals 1 times branches? 17. No, that's not right. The first one, so if we start from 0, the only branches should be 1 here, right? Like, because 1 is the only number. So when we get to the end, we want to add 1. Maybe that does need to be 0. No, that's still 16. Need to add 1. And then, no, we don't want to add, do we? If branches is greater than 1, counter times equals branches. Times equal branches. Nope, still 12. So at this point, there's just 1. At this point, there's still 1. Now, at this point, there's 3, right? 5, 6, and 7. We're going to times equals that 1 by 3 because we've forked at this point. And then here, there's 2 options here, right? So we're going to times for this 5. Yeah, for each number we want to multiply by the number of points that there are. I'm gonna call this calculate branches. Calculate branches. File name, right? Return counter. Calculate branches. Okay. No, let's not take file name. Let's take this as joltages just for now. So we'll say read data of that. Pass that in there. Because I just want to see, right, if I do calculate branches on 0, 1, and 2, there should be, the answer should be 1. No, that's wrong. Okay, so counter is 1. For I in joltages, branches no, okay, there's 2 there's 2 routes through this, right? That's fine. So we've got 1, 0, 0, 3, and 6. There's one route through that. 9, one route through that. We have 8 and 9, there's 2 routes through that. If we have 1, 4 routes through that. Yeah, that makes sense. Why am I getting 8 for that original sample? I'm just curious if I do it for here as well. Oh, that number is way too big. Something's getting inflated here. Is it because I'm sure there's a mathematical way to do this. But I think it's because there's situations where you're like multiplying, but it's not. It reduces the options, right? If we go to the length is different. Yeah, that's what it is. So I can't do it that way. We could count the number of next positions. It's kind of what I was doing here, right? Of calculating the intervals, but actually what we want to do is calculate the number of options that there could be next. We're skipping some. Right. I'm curious. What I'm going to do, I'm going to stop here. I'm going to see whether we could do all simple paths in cuGraph and just brute through this with the GPU. I think that would be the best, like, within the context of these videos, I think that would be the most interesting way to do it. That involves me going and talking to people. I think I'll probably raise an issue on cuGraph, ask about that, and then maybe I'll ping some folks inside NVIDIA. So I'm going to stop here. I'll stop the stream here. For those of you watching the video, I will be back very shortly with an answer. Hi everybody, it's the next day. I left NetworkX running overnight. It was probably running for about maybe 20 hours and it just hadn't finished yet. So this is definitely the wrong way to do it. I guess from like one of the things that it said at the end of the challenge is this is probably the wrong way to do it. I raised an issue on cuGraph to see whether there's like a cuGraph implementation of this. They kind of got back to me and said that the API hasn't been exposed in Python to do that. So, and also that it is the complexity increases as you make this list longer to like an undesirable point, and this is kind of, you know, hard, right? And it has if you write down like the computational complexity of this, it is an exponential problem. So what I've opted to do now, because my approach has kind of failed and I'm keen to just move forwards, what I've done is I just had a quick Google, found somebody else's solution, and what I'm going to do just for this part 2 now is I'm going to take this other person's solution who's worked out like the mathematical approach that I couldn't wrap my head around yesterday. Somebody's talking and it's Google in my pocket, I think, because I'm chatting away. Right, go away. Sorry about that. Instead of working out the solution, what I'm going to do is I'm going to take somebody else's solution and I'm going to make it run on the GPU. Now, I think the solution runs pretty fast as it is, but let's have a look at how we could do that on the GPU. So here's the solution that I found a minute ago. It's the part 2 that we're specifically interested in. So they've got their list of numbers. So yesterday we were working with our what do we call them, joltages, right? Their list of numbers here, and they make this dictionary called linkers, right? And they set each value to 1 for n in numbers, right? So it's basically an array of ones, but they're doing it as a dictionary just for the data structure. And then what they're doing is they're enumerating over those numbers, which this step is kind of what we do in CUDA, right? Is we effectively enumerate over an array of numbers. So we could definitely do that. And then they've got some nested logic here, which is updating the linker values. So what we would need to do is basically split this for loop out into like a CUDA call, and then here we would need to do an atomic add to make sure we can add to that. So I'm basically going to take this little bit of logic and then we're going to refactor it into CUDA. So let's copy the URL and put it in here and just say part 2 based on this solution but converted to CUDA, and let's just link that based on this solution there but converted to CUDA. Okay, so let's just get rid of everything I've done here because this is the wrong approach and it's not a good thing to do. So let's just copy that solution again. I'm not going to run this as it is. I know it will probably give me the right answer, but we've got our joltages here. Let's reset joltages back to be like a sample, right? So it will be sample like that. So then let's just copy some chunks of CUDA-y stuff. So we want to do this kind of thing. We want to calculate. What do we want to do? We want to calculate paths, right? We are doing paths through a graph, but we want to calculate the paths mathematically here. And let's do our kind of standard thing of set our output position to position. Oh, I think I've restarted a bit somewhere, so let's go like that. And then we'll do our threads per block and blocks per grid kind of thing, and we'll also copy where we calculate our output. So we'll go like that. Ooh. Not doing very well with my copying and pasting here, am I? Right, we run those, and it's now called calculate paths. That. Okay, so we now have a array of our things here. So what we're doing is we want to do our linkers here is going to be our output, and we want the whole joltages. So it's not actually going to be joltages -1, it's just going to be joltages. So here and here, that needs changing. And our linkers is our output array. So instead of zeros, let's do ones because they are doing ones. Like that. And then let's just take this bit here, put it into here, right? So we're not going to enumerate our numbers. What we're going to do, right? I is now position. So I equals position, and N1 equals joltages at position. And then we can get rid of this enumerate, right? Because we're doing this with the GPU now. Then we're doing for j in these things. If j is less than that, for n in this will be joltages, and that will be joltages, and that will be joltages. I'm actually just going to replace i's in here with position. Is that all the i's? And N1. Yeah, let's leave that as N1, right? So N1 and N2. We actually want output position. It's actually the output of N2, isn't it? N2. So we're actually updating the output array differently. And we want to do an atomic add, which we did in a previous solution. I'm just going to guess 5. No, it might be earlier than that. 3. Yes, atomic add. Oh, my headset battery died. Doesn't really matter, but let's keep going. Here we want to do cuda.atomic.add, and then it will be output is the array. 4 is the value, I think. Let's just have a look at this docstring, just so we can go doing index and value. Okay, so the index will be this, and then the number we want to add will be that. Okay. So I think that is effectively our code ported over here. So let's try running that and see what happens. Typing error. Good. Linkers is not defined. That's fine. That's because it's not called linkers, it's called output. Linkers there is called output. Okay. And then that solution, we wanted max numbers. So it's the last thing, isn't it? So -1. Let's do what they did. Let's go max of voltages. Curious to why, what's going on there. Index 22 is out of bounds. Curious, like part 1, 8. Maybe something's gone wrong in here. Right, I am just gonna run their code like this to see what we get. The numbers is actually voltages, right? Voltages, 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 voltages. Run that. 8. Okay. That logic worked. As you would expect. So what have we done differently here? Yes, this dictionary mapping is important. The fact that it's a dictionary is important. I don't want to be getting, yeah, this isn't an index, is it? The fact that for N2 in voltages, and then we want to update that value. It's actually going to be not N2, it's going to be mp.where output equals N2. Typing error, and do mp.where unsupported numpy function mp.where. Okay. I almost wonder if we need to do for k in output if k equals n2 I'll make add that. No, that didn't work. I get the feeling I can't run this in parallel actually because of the way this is running. I think we've got this bit of code here. I'm going to call this a loss. We're going to say actually, here's my answer. Oh, that calculated fast. Here's my answer. Let's come and plug it in. Submit. That's right. You got 1 gold star. Okay. All right. I think because of the linked nature of working through this it doesn't make sense to parallelize. So we've just copied the CPU solution here. Slightly disappointing, but it is what it is. Let's just, yeah, let's take 2 minutes to just tidy this up. Let's just change that to copied from this solution, and let's just get rid of all of that. I'm just going to say because of the linked nature of this calculation, it doesn't make sense to parallelize. Is that how you spell parallelize? It is in English, but okay. I'm British, so I'm going to put that there. Right. So, yes. That's disappointing, but let's just delete these things here. And I'm going to copy their code and save that. I'll push that up. Sorry, I didn't manage to come up with a GPU solution, but let's wrap it up there. And in my next video, I will hopefully do better with the next one.